All right, so chapter 6, we're going to actually start talking about static routing. We're going to talk about static routing implementation, how to configure static and default routes. There's going to be a review of CIDR and VLSM notation. Again, that's one of the hardest things in networking to me is remembering all of that. Luckily, you have gone beyond needing to manually subnet at this point in your life, and you can use the subnet calculator for this stuff that's not on the test. We're going to talk about floating static rules and summary rules, and then we'll talk about static and default routes. So we're going to talk about the advantages and disadvantages of static routing, the purpose of the different types. We're going to talk about IP4 and IP6 static routes, and IP4 and IP6 default routes. And then we'll talk about legacy classful addressing and the purpose of CIDR in that addressing. Then we will configure an IP4 and 6 summary network. We'll look at floating static routes. We'll look at how routers actually process these packets, and we'll talk about some of the issues that come up with that. As we go into this one, you're going to see that there's lots of places where there are commands. One thing I'm going to strongly suggest to y'all is that you go back and build you a little network in Packet Tracer and try some of the commands you're going to see here. If you haven't done so, go on Blackboard and download the Packet Tracer manual. There's some startups in that manual that'll give you some stuff that you can work with as far as how to configure some of this stuff. And you'll even find a couple in this chapter that are configured wrong for you to go in and troubleshoot to try to play around with. I think that'll be the best thing in the world for y'all to learn this stuff. So a router can learn about remote networks in one of two ways. Manually, where I tell it what the remote network is, or dynamically, where it uses a routing protocol to find out about remote networks. So static routes provide some advantages. A static route is not advertised over the network, so it provides better security. Static routes use less bandwidth than dynamic routing, and no CPU cycles are used to calculate or communicate those routes. The path a static route uses to send data is always a known path. So in contrast to that, there are lots of disadvantages to static routes. The initial configuration and maintenance is time consuming. In a large network, there is error-prone configuration because if you type IP addresses over and over and over and over, you're bound to type them wrong somewhere. Anytime the route changes, if something changes on the network, the administrator is going to have to go in and change the routes on all these devices. These do not scale well as a network grows because it becomes very cumbersome to add routes all the time. And they require complete knowledge of the whole network for proper implementation. If you're going to try to static route a whole network, you've got to know everything that's on that network to be able to do it. So static routing has three primary uses. It provides ease of a routing table maintenance in a smaller network that's not expected to grow. It provides routing to and from what's called a stub network. And a stub network is a network that has a single route and the router has no neighbors. Most of you at home, in fact, I'm going to say all of you. You all have stub networks at home, meaning you're on the end of a network. There's no routing going to take place through your cable modem except to you. Using a single default route to represent a path to any network that does not have a more specific match with another route in a routing table. Default routes are used to send traffic to any destination beyond the next upstream router. So that default route is, hey, I don't know what to do with this traffic, so I'm going to send it here. Static routes are often used to connect to a specific network to provide a gateway of last resort for a stub and to reduce the number of routes advertised by summarizing several networks as one static route. You can also use them to create a backup route in case a primary route link fails. So usually this is where you're going to use these, is for a specific network. If you're doing some routing that is a little out of the ordinary on one particular machine or on a set of machines, you may add a static route to get those machines just to specifically where you need to go. So here we got an example of a stub network. Stub router is R1 here, using 172.16.3.0/24. So basically we could configure this interface to know this is a stub with just a single route command, and say anything that you don't know what to do with, send to 172.16.2.0. A default static route is a route that matches all packets. A default route identifies the gateway IP address to the router to send all packets it hasn't learned or doesn't have a static route for. A default static route is simply a static route with 0000/0 as the destination on the IP4 address. So that's how you configure that. You assign 0000 to an IP. So here they're showing using one summary route. If I represent all four networks here, 172, 20, 21, 22, and 23 on 16s, you can use one summary route, 172.20.00.14. So this is where all of that stuff on subnetting actually comes into use. You can combine these to represent these networks in a single command. Now, would you be able to issue the command to say that these are each individual static routes? Yes, and that'll work perfectly fine. But if I wanted to summarize it to not have as many commands, I could do that as well. So a floating static route is a static route that's used to provide a backup path to a primary route in the event of a link failure. Floating static routes are only used when the primary route is not available. To accomplish this, the floating route is configured with a higher administrative distance than the primary route. One place that this is used quite often is in backup networks. I use the network over at LSUS a lot because I'm pretty familiar with it. Over there was a backup route on DSL, and it was much slower than our connection to Lonnie. So it had a higher administrative distance assigned to it, so that the other route had to be down before it would be used. And since it was so much slower, it wasn't used for round robin or anything. Round robin is where you have two interfaces that are the same speed and have the same administrative distances. So traffic will go out one then the other to kind of speed things up. But with a slow connection like that, you just have it as a backup. So the IP route command, IP route space network address space subnet mask, is what you use to actually assign a static route. The next hop can be identified by an IP address, an exit interface, or both. The next hop route is only the next hop IP address being assigned or being shown. If it's directly connected, only the router exit interface is specified. And if you fully specify it, then you put the next hop and the exit interface. So here they want to give you an example. When a packet destined for 192.168.2.0.24 comes into router 1, it looks for a match in the routing table and finds it has to forward the packets to the next hop, 72.16.2.2. Router 1 must determine how to reach 172.16.2.2. So it searches a second time for a match. So here it finds 192.168.2.0 being directly connected. In a fully specified static route, both the output interface and the next hop are specified. This is another type of static route that is used in older iOSs. So this was only used in some of the older versions. You're not going to see any of this in the new iOS 11. This form of static route is used when the output interface is a multi-access interface and it is necessary to explicitly identify the next hop. The next hop must be directly connected to the specified exit interface. So again, some commands that you can use here: show IP route static, and show IP route network will give you some ideas of what's going on. Here, if I want to configure that default route, I'll do an IP route of all zeros. Notice they spelled it out 0000 with subnet 0000. You could do a /0 in there. And then the IP address that it's going to go to and an exit interface. So here to configure a default static route of 172.16.2.2, I would assign to router 1 an IP route of 0/0 to that interface. Now when I have traffic, it's going to try to go out there. And notice if I do a show IP route, I'll see the gateway of last resort is set. So IP6, same thing, except we're dealing with IP6 addresses. They'll have a standard, default, a summary, and a floating rule. The next hop can be identified, the exit interface, all just like IP4. Here we've got an example of an IP6 route on a fully IP6 network. And here again, a directly connected static route. These are all /64 networks, which are pretty standard now for IP6s. I know that somewhat seems like a waste of IP addresses, and in a way it is, but there are literally so many IP6 addresses, this should not be anything that we ever worry about. So to look at your IP6s, use the same command, but instead of just IP, add the v6. Show IPv6 route, show IPv6 route static, and network. Now here to set the default route on IP6, we're going to use the address ::/0. So here they're setting IP ::0 to this IP address, 2001 DB8 ACAD 42. And here we're verifying it. We can see that we have a route ::0 statically set via, and then the IP address of the link it'll go out. So a brief reminder, classful networks, class A's start at 0, end at 127. I kind of like to end it at 126 because, 127 is a special address that can't be used for anything. Class B's 128 to 191. C's 192 to 223. Your D and multicast are 224 to 239. And then reserved are 240 to 255s. Chances are you're going to be working with a private address in one of these spaces. Unless you're actually working for an ISP, you're probably not going to be working with that many public IPs. You'll just have public IPs in your server room, and you'll maybe assign them to devices in DMZ, or you'll use them to use NAT to send things through to your local network. So here again, a class A, the subnet 255.000, a B, 255s, and a C3. And that comes from the bits that are used on the network and on the host. So classful routing example, they're showing 192.168.2.0.24. through on 172.16.1.0 and out on 16.0.0. So the problem with classful addressing is that it's terribly inefficient. That's what's led to a lot of the problems we have on the internet today. There are tons of addresses that could not be in use until things were subnetted because some organizations that had a Class A were only using a few of those IP addresses. If you look here, a Class A has a maximum number of 2,113,928,964 IPs. Okay, that's a whole lot of computers, and based on when you were given that Class A, maybe you've only got 5,000 machines, so you're wasting so much of that before we started subnetting. With B, you've still got pretty big networks, and then C, you've still got pretty big networks too. So this is why we switched to CIDR. Classless interdomain routing is more efficient than the classful routing. And with CIDR, again, we can summarize using SuperNet routes. If we have all of these routes that are 023s, we've got, looks like .8, .4, .2, and .0. We can SuperNet that into 192.168.0.0/20. If you are a little unclear on that, what I would strongly suggest you do, there is a Google site called Subnet Calculator. I think it's the first one that comes up. Go to that and put these addresses in and look at the SuperNet, moving the bits to see how they got this. There's lots of examples on there to make sure you understand that. Again, you don't have to do that. You could issue 4 static route commands here and it would work just fine. So here they're just showing again using a summary route table. And to summarize these 255 networks, we're going to get 1 248 network. Here we're just looking at the same thing. So when we look at a basic subnet scheme, we see that the subnet portion is the part of the host that we're using to assign to the network to break the host down. Here in this example, one subnet was further divided to create 8 smaller subnets of 2 hosts each. So notice that subnets can vary in size as well. So VLSM allows for the different masks for each subnet. After a network address is subnetted, those subnets can be further subnetted. I touched on this the last time I taught 101 because it's something that I knew was coming in this class. But you can basically subnet a subnet. So here they say think of that as sub-subnetting. Individual host addresses are assigned addresses from the sub-subnet. So here we've got our first round of subnet. We're breaking that down into a second set of subnets. Here we're going to break that down even a little more for separate buildings. The important thing to know at this point with that is that you can subnet subnets and then you can subnet those subnets. Now, unless you're dealing with a really big network, this may not be anything that you ever look at. But if you're dealing with a huge network, you may find a need to subnet it more than you're able to do with just a Class A of addresses, especially if you're going to use a private Class A. Or it may be something that was already set up that you're going to have to go in and work with someone else's work. So another term to be familiar with is route summarization. This is also sometimes called route aggregation, and it's the process of advertising a continuous set of addresses as a single address with a less specific, shorter subnet. CIDR is a form of route summarization and is synonymous with the term supernetting. So this is taking your networks and basically unsubnetting them for your router advertisements. CIDR ignores the limitation of classful boundaries and allows summarization with masks that are smaller than that of a default classful mask. This type of summarization helps reduce the number of entries in routing updates and lowers the number of entries in local routing tables. Again, this becomes important if you're dealing with a big network. Instead of having all these networks that have to send out their data every time anything changes, if the route is summarized, less has to go out between the routers, and the routing table will contain less information, which ultimately makes it faster because there's less table entries for each packet to need to look through to find out what port it needs to go out. So here we're showing how to calculate a summary route. So the way we do this is count the number of far left matching bits to determine the mask. So here we have 14 matching bits. So a 14 is a 255.252.00. Copy the matching bits and add 0 bits to determine the network address. So our network address here is 172.20.00. So here they're just giving an example of using a summary static route. Aside from the fact that IP6 addresses are 128 bits long and written in hexadecimal, summarizing them is similar to the summarization of IP4 addresses. It just requires a few extra steps due to the abbreviated IP address in hex conversion. Now, think back to Cisco 1 where we talked a little bit about how IP6s are written. And remember, the two colons together summarizes that there's zeros in there. Multiple static IP6 routes can be summarized into a single static 6 if the destination networks are continuous and summarized into a single address. The multiple static routes all use the same exit interface or next hop for IP6. So there are 7 steps to summarize IP6 networks into a single prefix. First, list the addresses and identify the part where they differ. Expand it out if it's abbreviated. If it's abbreviated, take all those and write it all the way out the way it should be. Convert the differing section from hex to binary. So this is something that you can do directly, but because I am not real strong at math, the way I do this is convert it from hex to decimal and then decimal to binary. Count the number of far left matching bits to determine the prefix length. Copy the matching bits and then add the 0 bits to determine the summary. Convert it from binary back into hex, which again I would go through decimal, and append the prefix. So that's finally the result of step 4. So here they are giving you an example of this. To be honest, make sure you're aware of this and how it works. But it's something that if you've not worked with IP6, you've probably never seen before. So don't spend a tremendous amount of time on it. Just be aware of it. Play around with some of the packet tracer files and see if you can figure it out. Floating static routes are static routes that have an administrative distance greater than the administrative distance of another static route. This is increased to make the route less desirable than that of another route or a route learned through a dynamic protocol. In this way, the static route floats and is not used when the better administrative distance route is alive. So this is again for your backup links. You set it as if it's floating because that administrative distance is higher, or based on what protocol, we can call that cost as well, is higher. So that route sits there and is not going to be used as long as routes of lower cost are available. But if your primary route goes down, then the floating route can take over based on its administrative cost. I'm going to see if the next slide says it, but you can have more than one floating static route. If you have super mission critical that you have internet access, maybe you've got a primary and then two backup links. And one backup link is cable at 10 megabits, and then your other backup link is, say, DSL at 5. Well, you can set the administrative cost of your fast route first. Then you can set the one for your cable connection to be higher than that, and set DSL higher than that. And in that case, it will continue to use the best route till it's lost. Then it'd switch over to cable, and if cable and the best route were lost, it would switch over to your DSL connection. So here we're showing just how to set a floating route. And here we've got our administrative distance out here on the end. So to test a floating static route, use a show IP route command to verify the routing table has a static route. Use trace route to follow the traffic flow out. Then disconnect the primary, or if you don't want to physically disconnect it, issue a shutdown command on that interface. Then do a show IP route and a trace route again to see that it actually switched over. So here we just got another example. So again, common troubleshooting commands include ping. You can issue ping and trace route both from a computer connected to your router or from the router itself. Based on what operating system, it'll be trace route or trace RT. If you're issuing it on a switch or a router, you're going to use the full trace route. But if you're doing this on Windows, it's trace RT. Show IP route, show IP interface, and show CDP neighbors detail will give you some more information. So in solving a connectivity problem, finding a missing route is a relatively straightforward process if the right tools are used in a methodical manner. First, use ping to confirm it can't be reached. Then trace route should reveal what the closest router responds to or fails to respond to. In that case, the router is sending the ICMP messages, those pings we talked to the other routers. The next step is going to be to investigate the routing table and look for missing or misconfigured routes. And then incorrect static routes are a common cause of routing problems. Again, the thing about IP addresses is you type one number wrong and you've got your whole thing shut down. So here they're showing we're not getting a response. Success rate is 0% on those pings. So in that previous slide, the user at PC1 reports he cannot access resources on the R3 LAN. This can be confirmed with a ping. Trace route would reveal that R2 is not responding for some reason. It's forwarding the trace route back to R1, which returns it to 2. If it were not for the time to live value, this loop would continue. So that's why there's a time to live, by the way. It's to keep these routing loops from existing forever. So the next step is to investigate the routing table of R2. If you were to do that, the routing table would reveal that 2.0 is configured incorrectly. A static route has been configured to the next hop of 2.1. Using the configured next hop, the packets destined for 2.0 are sent back to router 1. So there's the problem. It's connected to 3, not 1. Therefore, the static route is wrong, so one IP address wrong causes the whole thing to shut down. So in Chapter 6, we talked about these static routes. We talked about next hop. On point-to-point serial links, it is more efficient to configure the static route with an exit interface. On a multi-access network such as Ethernet, both a next hop and an exit interface can be configured. Static routes have a default administrative distance of 1. I don't know if I went into that or not, but they do have a default administrative distance of 1 unless I change that. So a static route by default is going to be preferred over other routes. A static route is only entered in the routing table if the next hop IP can be resolved through an exit interface. And in many cases, several static routes can be configured as a single summary route with supernetting. The ultimate summary route is a default route configured on 0/0. There is not a more specific match to the routing table because 0/0 is going to match everything. A floating static route can be configured to back up a main link by manipulating its administrative value.